Okay, well, let's go ahead and get started. I am happy to introduce Dr. Alyssa Winter-May. She has been operating our MALDI time of flight for some time now, and I think many of those that are on the call have probably been trained by her. So today she's going to be presenting on MALDI-TOF mass spectrometry and macromolecular analysis. Alyssa, take it away. Thank you.
Thanks, Corey. Hopefully this will be fun for some people and you'll learn some things. I am Alyssa and we're going to talk about MALDI today. All right, so what are we going to talk about? What can we do with MALDI-TOF? How does it work? What are some applications we can use the MALDI for? A little summary of our core facility instruments and services. And then finally, in the end, we'll take some questions. All right, a little bit about me. I did my PhD here at CSU in graduated in 2021. My PI is Professor Travis Bailey, and I'm a synthetic polymer chemist. So get ready to talk about some polymers today. My research focused on making synthetic polymers, block copolymers for ion gels and energy applications. Now I'm a soft materials postdoctoral fellow at the ARC. What does that mean? Well, I manage the MALDI. I do full service. I do training. I maintain the instrument. I also, help consult with customers who have soft material problems and questions. So, feel free to reach out at any time if you have any questions for any sort of analysis of polymers or other soft materials or macromolecules. I'm also the associate director of, because I don't have enough jobs, the associate director of the Materials Science and Engineering Core Facility. We focus on materials fabrication, characterization, and synthesis. I'm also a human in real life, so I like to get outdoors, play sports, do hiking. I have an extremely handsome cat that I'm obsessed with, so if you see a bunch of cat pictures, don't be surprised. And then I'm also apparently the same height as my instron in the materials core facility. So what can we do with the MALDI-TOF? Well, there are so many applications of MALDI. This is not a complete list. This is just some of them. This is also a picture of the fleet of Brooker MALDIs. I promise Brooker is not paying me to do this talk, but there's so many things we can do. We have a super wide variety of customers at the ARC using the MALDI for lots of different applications. So a little bit later, we'll just highlight some of those. But I think the MALDI is one of those really flexible, versatile instruments that can help a lot of people get some really interesting information, and they might not realize that the instrument is actually useful for them. So a couple of the applications we'll talk about today are polymer analysis, peptides, protein digests, small molecules, intact proteins, nanoparticles, and oligonucleotides. And that's not comprehensive for what people do here, but it's just a little taste of it. Okay, so what kind of information can we get out of the MALDI? We can, it's a time of flight mass spectrometer, so we can get an accurate or intact mass of whatever we can get to ionize on it. But there's a lot of polymer qualities that we can assess with the MALDI: molecular weight, identity, dispersity, end groups, structure. A lot of things we can learn about polymers from it. Peptides, we can get masses, sequence them. We can assess functionalization of any molecule that will, fly on the MALDI. And then there's so much more, but, not a comprehensive list. What are some benefits of the MALDI? One, I think, is really that it's super low cost. It takes as long to get data as it takes you to acquire a spectrum, which can be seconds. And because it's super fast to acquire data, that means it can be pretty low cost. You can do a ton of samples in a really small amount of time. So if this technique really works well for your samples, you can do it really fast. We have super minimal sample requirements because the instrument is extremely sensitive. So if you only have, a couple of nanograms of material, you can get data. Sample prep can be really quick once you know what you're doing. There can be some method development associated there, some time there, but once you know what you're doing, it's really quick. It's as quick as just dropping some droplets onto a plate and letting them dry. It's also really great for compounds with limited solubility or high salt content, right? One of the big limitations of LCMS is you're limited to whatever solvents are appropriate for the chromatography system. And with MALDI, we are solvent agnostic. We don't care what solvent it is, as long as you can dry it off the plate before we put it in the instrument. We can measure intact molecules, macromolecules like proteins, because it's a soft ionization technique and we don't typically produce fragmentation, but also because MALDI tends to produce low charged ions like 1 + 1 + 2. We can get really high mass accuracy even for fairly large macromolecules. So that's molecular weight dependent, right? The higher the molecular weight, the lower the mass accuracy, but we can get pretty decent for, depending on what your application is. Okay, so you're thinking like, wow, MALDI's so great. Why don't we just use it for everything? Well, it's not a perfect technique, but there's no perfect analytical technique. That's why you have so many of them, right? But some of the disadvantages here, complex mixtures are hard to analyze. We don't have a chromatography system on the MALDI. You have to do, if you need any separations, you have to separate things ahead of time. Our limit in terms of doing fragmentation in MSMS is about 5 kilodaltons. The sample prep is a lot of just spending some time figuring out what works for you and your particular samples. We don't have high resolution across the board. The instrument can handle pretty high molecular weights, but high resolution, a high resolution mass spectrum that people typically think of is really only relevant for molecules less than 20 kilodaltons. If your sample or species happens to become highly charged in the MALDI, it can be a little difficult to ionize, but that's a pretty rare circumstance. If you're trying to analyze polymers, the best case scenario is that they're low dispersity. We'll talk about what dispersity means later, but if you have really high dispersity polymers, it can be tricky to get all the possible information out of the MALDI spectrum. And then if you have some complex copolymers or complex polymer architectures, that can also be difficult to analyze. And then I think what people don't realize is, a lot of instruments, they want to just prep their sample and throw it on the thing and shoot it and get data right away. It takes time to learn. The data acquisition of MALDI is fairly manual and requires some time and getting acquainted with the system, getting comfortable with it. So, it can be, it's not a super low barrier to entry if you want to get your own data, but it's not hard to do once you know what you're doing and you've practiced a bit. So anyone can do it. You just have to take the time. Okay, so basics of MALDI-TOF. I think every polymer talk would be remiss if we didn't just do a really brief intro to mass spectrometry in general, if you're not a mass spec person. Pretty much all mass spectrometry systems share a couple things in common. We have some kind of sample inlet, an ionization source, mass analyzer, an ion detector, the source, analyzer, ion detector, and data system, usually some kind of computer. So why do we have an ionization source? Because we need to analyze molecules and detect them on a detector. We need to get them to fly through a vacuum. So we need to ionize them using the source, and then in the mass analyzer, we'll sort them by their mass to charge ratio. So all MALDI spectra that you'll see in the following talk are, your x-axis is going to be mass to charge, which is your mass of your molecule divided by the charge that it picks up in the spectrum, in the source. So how does that relate to the MALDI? Well, first of all, what is MALDI? What does it stand for? It's a term I've been throwing around for a few minutes already, but matrix assisted laser desorption ionization, time of flight. All right, what does that mean? Well, first thing in our mass spectrometry primer, our sample inlet, unlike other mass spec systems, our sample inlet, instead of being a chromatography, like a liquid chromatography or gas chromatography system, we just have a stainless steel plate. Right, I mentioned there's no chromatography, we can't do any separation. So whatever you put on the plate is what we're going to get a mass spectrum of all at once. So once we've gotten it into our sample inlet, then comes into play the MALDI part of it. And the MALDI is our ionization source. We're going to use a laser. We're going to get our samples ionized with help from the laser and the matrix. We'll talk about how that works a little bit. And then the time of flight component is our mass analyzer. So time of flight, it's pretty similar to all other time of flight instruments if you've learned about that before. But once we get our samples ionized, we use a high voltage to accelerate them through a high vacuum flight tube. And they travel through the flight tube based off of we measure their mass using the time of their flight through the flight tube. Heavier molecules go slower, lighter molecules go faster. So the time it takes them to hit the detector is how we correlate that to an actual mass. All right, we need to get molecules ionized so we can accelerate them into the flight tube. How do we do that? First, we take our sample that's in these little green dots. We co-crystallize them on that little stainless steel target plate that you saw before. And then we shoot them with a laser. In this case, it's a 355 nanometer modified ND YAG laser. After we shoot the laser, the matrix molecules will absorb that UV energy. And then in a kind of Goldilocks scenario where just the right amount of UV energy is hitting it, our matrix molecules will absorb that energy and then transfer the energy to our analyte, initiating the desorption of the analyte. So the matrix assisted part of this is that the matrix is what's absorbing that UV energy. And so our molecules on the plate don't just get totally destroyed by it. Once everything is desorbed and in the gas phase, then collisions between the matrix and also probably some ionization agents causes charge transfer. That's how we get things ionized. And then once everything is ionized and in the gas phase and hanging about, we use high voltage acceleration. We use a high voltage differential to accelerate our ions. This pulsed ion extraction is a clever way of giving time to the molecules to all get ionized and uniform. It's typically about a 200 to 600 nanoseconds after the laser pulse and before the high voltage supplies in the instrument pulse and cause that acceleration. Okay, so what's a matrix? I've said the word matrix a lot. Well, matrices are a couple things. They're small molecules with just the right molecular weight. They're big enough to not immediately evaporate. They're small enough to volatilize. More importantly, you may notice that they're all typically pretty conjugated, high conjugation in these systems, lots of aromatic bonds, triple bonds, double bonds. That makes them strong UV absorbers. If you look at my drawer of MALDI supplies, you'll notice a lot of them are yellow. That's pretty typical of UV absorbing compounds. Because they're strong UV absorbers, they can do that thing we just talked about before, where they absorb the UV energy so your sample doesn't break apart and degrade in the source instead of ionizing and desorbing. So We have a bunch of different matrices here. They're all good UV absorbers. That's required for a matrix to be a good matrix. Well, in addition to absorbing a lot of UV, there are also potential electron acceptors, which can also help with the ionization process. And a lot of them are also acids. So for instance, like this alpha cyano for hydroxycinamic acid or 2,5-dihydroxybenzoic acid, those are, they can be proton donors and help some of our more polar analytes protonate. And so we can run MALDI on them. Okay, so which matrix do I choose? How do you know? Well, you have to pick a matrix based on your application. And I'm not going to go over what matrices go with what applications. There's tons and tons of them. But, it's well established. There's a lot of really common matrices that are typical choices for applications. DCTB over here that we saw on the last screen is typical for polymers, synthetic polymers. HCCA is a typical matrix used for peptides or some low mass proteins. There's so many different ones. A lot of it is either searching the literature or trial and error. So because of that, it might take some sample prep method development to figure out what's going to work well for your sample. If you ever run MALDI and your sample doesn't work the first time, that's okay. That's happened to a lot of other people in the world. So you're not the only one, and you're not bad at what you're doing. That's normal. Okay, so good for you. You picked a matrix. What do we do now? Well, we got to get it on the plate so we can get it into the sample, into the instrument. We have two different types of plates. In the ARC right now, we have these 96 well plates, which are nice when you're just running a couple samples. We have these 384 spot plates that are great for when you're doing a ton of samples. Either one works. Notice that they're stainless steel because they actually become part of the ionization source in that high voltage is applied to them. So stainless steel, you can't just put anything in the MALDI. It has to be these particular stainless steel target plates. But you can put anything on the stainless steel target plates. So an example for synthetic polymers of a sample prep strategy, you would take DCTB and high concentration NTHF, mix that in a microcentrifuge tube with a little bit of polymer solution, a little bit of salt, mix it together, and you just drop it on the plate and let it dry, and it will spontaneously crystallize. Depending, that works really well when you have that particular sample prep works great for synthetic polymers, but the dry droplet technique is great for samples that everything you're trying to put together on the plate are all miscible. If you don't have necessarily everything miscible, you can do like a layered example where you spot your sample on the plate and then you let it dry, and then you spot the matrix on top and let it dry. This would be an example for peptides where you're mixing, your sample is in 0.1% TFA solution, and then you overlay matrix HCCA solution on top. Now, in this case, those two solutions would be miscible, but it's, for whatever reason, maybe the layered approach works better than the dry droplet. There's lots of different sample prep strategies. These are just two examples of them. All that really matters is that in the end, the plate is dry because we can't put wet samples into the source because the source is under high vacuum. So if it's under high vacuum and you put a super wet plate in, what's going to happen is your vacuum is no good anymore because you're just evaporating off liquid. Okay, so we've got our samples on a plate, but wait, what if I can't get my sample on a plate because it won't go into the solution? So what's my sample? If my sample isn't soluble, we've got a solution for that. Solution. So you first, step one, you grab an agate mortar and pestle, which we have one of them in the ARC, right, waiting for anyone who needs to use it. And you put a little bit of your powdered sample in the agate mortar and pestle. Then put on a whole bunch of matrix. This is not particularly quantitative, just be aware. This is just you eyeball it. So a little bit of sample, a lot of matrix, and then believe it or not, this is a different picture. There is a slight amount of salt on top there. So once we have our matrix, sample, matrix, and salt all mixed together, or all in the mortar and pestle, then we mix it. Then once we've got a nice, good, uniform mixture of powdered material, then we take that little plastic spatula and actually just scrape it up and smear it on the plate and dust off any excess. And that's it. And it's already dry and crystalline and ready to go. Okay, so our sample's on the plate. We want to run MALDI. We've got it in the instrument. We've got our sample ionized. Now we need to run it through the TOF. How does the TOF work on this instrument? Well, you've probably learned a little bit about time of flight mass spectrometry before. And for the most part, time of flight on the MALDI-TOF works the same way as you've seen it before. The difference, there's a couple big differences. In this instrument, we happen to have an axial TOF configuration where instead of like a typical LC QTOF or something, you would see an orthogonal configuration where your source is 90 degrees to your flight tube. Here, our source is actually in line with the flight tube. So the nice thing about that is that allows us to minimize the amount of ion optics that we have to use to get our samples into the flight tube. So MALDI is also really great for things that are particularly labile that might just totally break apart in the QTOF process of getting a molecule all the way from the ESI source all the way to the flight tube. So it's really just source is right here. Target plate is part of the acceleration into the flight tube process. Ion source 2 is a small stainless steel plate a couple millimeters away from our target plate. And then when we need to accelerate everything into the flight tube, that ion source 2 will pulse down by several kilovolts in voltage, because what I guess I didn't mention is that the entire source, while the laser is pulsing and everything is ionizing, desorbing, the entire source is under high voltage. So everything sits at an ambient voltage of 20 kVs. And then when we're ready to accelerate ion source 2, this plate right here pulses down by several kVs, which causes the electric field gradient that accelerates our ions into the flight tube. So a couple different ways we can measure things. What you've probably learned the most about time of flight in a reflectron configuration. So we have a reflector detector on this instrument. And so our flight path is from the source all the way through the reflectron, which is a series of high voltage grids, which turns our molecules and then hits a reflector detector on the side. This is great for high resolution. A lot of, anything small molecules under 20 kilodaltons we're gonna get really nice data on the reflector detector. One of the big differences between this instrument and a lot of other TOF configurations you've seen before or learned about is our linear detector. Most TOFs only have a reflector detector. So the linear detector, well, why have it if the reflector detector is so great? The linear detector is low resolution, but it allows us to observe molecules that we would never be able to see on the reflector detector. Think of, any sort of giant molecule that has way too much momentum and can't make that turn. We're going to be able to see it on the detector, so on the linear detector. So that's why this instrument is capable of observing molecules up to about 500 kilodaltons. If we can get them to desorb and ionize, you can observe them on the linear detector. So linear detector is really great for a lot of applications, and in a lot of ways, it's great well, we'll talk about that later. But there's a lot of reasons why you would run the linear mode and reflector mode on the same exact sample. And then, okay, so this is a TOF. You've probably heard that it can do MSMS. Well, the thing is that there isn't a second flight tube. So if you open up the instrument, you'll notice there's only one flight tube. But we can still do TOF with that with some clever strategies. It's called the lift module. So in a QTOF, you would fragment ions in a quadrupole. I'm sorry, you would mass filter in a quadrupole, then you would fragment ions in a collision cell, and then you would do time of flight mass spectrometry in the end. Well, here we're going to do time of flight mass spectrometry first using the reflector detector of a particular sample. We're going to see peaks for every single ion in that particular sample. And then we say, okay, so first we run reflector mode. Then we say, okay, I am interested in this particular ion, parent ion 1. So then you tell the instrument to select parent ion number 1. And then we turn on the fragmenter, which is a collision cell filled with argon right at the end of the source. And when we do that, we reaccelerate the sample, but we're actually accelerating and fragmenting the entire sample all together after the source, because we don't have any way of mass filtering here directly post source. But then we have what's called a precursor ion selector, and it is going to select your parent ion of choice after everything has been fragmented. And it's going to catch the parent ion 1 and its fragments and let everything else fly through the TOF and get pulled out by the vacuum. And then it's going to, this lift module is another high voltage power supply, and that's going to re-accelerate your parent ion 1 and its fragments into the flight tube. So in MSMS, it's called TOF because we do time of flight 1 in reflector mode all the way from the source to the reflector, and we do time of flight 2 from the lift to the reflector detector. So because it requires a reflector detector, it's really only good for small molecules of about 5 kilodaltons or less. There's a couple of different ways we can do some clever things with MSMS of larger ions like proteins, where you can use the laser to fragment your sample into smaller fragments and then do MSMS using with the small molecule range fragments of an intact protein. Okay, so that's time of flight. Let's talk about our specific instrument, the Bruker Ultraflex Stream MALDI-TOF. So if you've been around in the ARC basement, chemistry basement main lab, you've probably seen this giant box. If you ever want to see what it looks like in person and see the guts of it, it's a particularly fun instrument to show people, because right here is the lid, and the lid raises up and shows, and you can see the inner workings of this instrument, which is really cool. But little specifics about the Bruker Ultraflex. We can get really fast results with the 2 kilohertz with a 2 kilohertz laser. We've got really good mass accuracies, especially for pretty big molecules. It's got very high resolution in reflector mode, and in linear mode, you're restricted to low resolution, but it's good enough for a lot of applications. You really don't need a lot of sample volume, especially because you're just putting a tiny amount on a plate. And if you have a lot of samples, we can put 384 of them on a plate at once. If you are doing really high throughput experiments, we can set up automation methods. Okay, so let's get to the fun stuff. Let's talk about some data. All right, MALDI-TOF applications. And many thanks if anyone is tuning in, to all the people who gave me data for this talk, or help, let me share their work. So, you might be used to seeing kind of more small molecule mass spectrometry. I think this is a really good example of that. Maybe you take issue with 1,000 Dalton molecules being small molecules, but to me they are. So this is an example. Alex Claiborne in the Hill group was measuring some functionalized beta cyclodextrins, and he was able to get really nice high resolution data confirming his functionalization. And the beauty of this is, right, it's just he can acquire this data as fast as he can spot it on the plate. So, you know, instead of doing long LC runs or whatever, you probably could acquire this data in about 5 minutes, which is really cool. So really nice high resolution, high isotopically resolved peaks you see in the left corner here, and then we can see the main unfunctionalized cyclodextrin here, and then the two main functionalized cyclodextrin peaks at 1200 and a little over 1300. Okay, another group of major MALDI users seem to be a little frozen. Okay, another group of major MALDI users are the Ackerson group. So Richard Reyes and the Ackerson group got this data. He was working on atomically precise gold nanoparticle materials, and he was investigating ligand changes, and he was able to observe really nicely every stage of the ligand exchange when two of these PET ligands were swapped out for one of these S3H6S's. So really nice example of some nanoparticles. The Ackerson group uses the MALDI all the time. Okay, so I'm a polymer chemist, so I wanted to spend some time talking to you about polymers and all the really cool stuff we can do with the MALDI and polymers. So if you are not a polymer chemist, then hopefully you enjoy this a little bit. So a lot of the terms I'm going to throw out, I'm going to explain right now. A monomer is just a single small molecule that we can polymerize. So when we do whatever reaction it takes to get them into a chain, now we've got a polymer chain, or in this case, this would be a homopolymer. But it's usually not as simple as we just take monomer and we string them together. Usually there's some kind of initiator molecule to start the reaction and some kind of end cap molecule. So because of that, we end up, we need to be able to characterize these end groups on a polymer chain. Once we've got, when we've got a polymer chain, there's a lot of ways we can describe polymer chains. One of those ways is degree of polymerization. So how many monomers did we chain together in this polymer chain? So in this case, my molecule would have a degree of polymerization of 14. That does not count the end groups. Oligomers is a term we'll use. You know, if you're a biologist, you might think of oligomers as like DNA or RNA oligomers. We use that term in polymer chemistry also. Typically, those refer to polymer chains with just a few repeat units, like a dimer or trimer. But for the purposes of this talk, I'm going to talk about any oligomer is something where it's a polymer chain with a specific degree of polymerization. So like a 70 or a 25, or, you know, any particular specific polymer, because polymers could be a single chain or a group of chains. Okay, so polymers. Like I said, polymers are never just a single molecule. We never have just a single molecular weight. We need to be able to talk about polymers in terms of a collection of polymer chains that have representative molecular weights. So it's not just one polymer chain with one particular degree of polymerization, it's multiple polymer chains with multiple different degrees of polymerizations. So here in this example, we've got 14, 10, 18, 9. Those are all come together to be one polymer. Because our polymerizations, you know, I wish we could make them super precise, but the nature of polymerizations is that you just end up with some variety of chain lengths. Okay, so if I wanted to measure the molecular weight of a single polymer chain, that's easy. I'm just going to add up, let's say my monomer mass is 100. I'm going to take 100 times my degree of polymerization, so 1400 plus the mass of my end groups, In this case, let's say they're 100. So my oligomer weight in this case would be 1500. So I have a bunch of different different oligomers with a bunch of different masses. So there's a couple of different ways to describe the collective mass of a group of polymers. One of those is the number average molecular weight, or MN, which accounts for the just straight average mass for each, for the number of chains we have. And when we have an MN of a polymer distribution, that represents equal numbers of chains on either side of the distribution. When we have a weight average molecular weight, that takes into account heavier chains contribute to the molecular weight more. And so when you have a MW, on either side of my MW, we have equal masses of polymers, even though it's not in the center of the distribution of weight. Okay, so why is that important? Because we want to use MALDI to measure all of these things and polymer dispersity. Dispersity is a really important measurement for performance of polymers, physical performance of polymers. So we can measure dispersity by comparing how big is our weight average molecular weight to our number average molecular weight. And it's literally just dividing one over the other. So I talked a little bit before that MALDI is really good for measuring low dispersity polymers. That is important because, yeah, we need our polymers to be about 1.2 or less if we want to be able to characterize quantities like this. That's not to say you can't characterize higher dispersity polymers in MALDI. You totally can. You just won't get a nice Gaussian looking distribution the way we'll see in a minute. Okay, so for polymers, why am I telling you this? Why do we want to know these things? Well, all of these quantities, polymer type, composition, molecular weight, structure, dispersity, chemical functionality, they're all things we can learn from the MALDI. A lot of these things are things we can learn from other techniques, but a bunch of other techniques, or we'd have to combine a bunch of other techniques, or they might not be as accurate. Or, in some way, sometimes, there's a lot of reasons why you just can't run that technique at all, solubility or various other issues. So, or the ability to calibrate or things. So we need to know all of these things about our polymer because all of those things have implications in the activity of our polymer, morphology, processability, mechanical properties, and more. Like how the polymer physically behaves is super dependent on all of these things we can learn from MALDI. And all of those things, reactivity, morphology, processability, mechanical properties, have huge implications in what their application space is. Are we going to use it for adhesives or fibers or rubbers or safety applications, right? If your polymer is too soft, you certainly can't use it in a bulletproof vest. So all of these things I need to know, and that all of these important information starts at the characterization phase in an instrument like the MALDI. Okay, so now let's get to looking at some data. Okay, so polymers, how can we identify a polymer using the MALDI? Well, this is an example of literally a raspberry clamshell container that I cut up a bunch and soaked in chloroform. And, the clamshell tells you it's polyethylene terephthalate, but how do we know? Well, the sample didn't fully dissolve, which is what I expected because the high molecular weight chains of PET were not soluble. However, we were able to observe low molecular weight oligomers, which allowed us to identify those as PET chains. PET is 192 molecular weight. And remember that whole talk about monomers? Well, the way we can identify a polymer in a MALDI spectrum is by looking at the distance between polymer peaks. So if you notice here, I labeled every single these regularly spaced peaks with the annotation tool in the MALDI software, and it's able to tell us based off of data I have in this building block editor that this spacing of monomers, right? Maybe this is a degree of polymerization of maybe 7 or 8, and then this would be let's say this is 7, this would be 8, this would be 9, this would be 10, this would be 11, because every time we add one monomer unit, we grow the chain. So we're able to identify polymers basically just by the spacing of our monomer units. This is an example of data acquired in reflector mode, where this particular oligomer here, when we zoom in, we actually have really nice data. We're able to see the isotopic envelope of that monomer at oligomer at about 2,000 molecular weight. Okay, so how do we do identification of polymers in linear mode? Well, it's the same thing. The only difference is we don't have isotopic resolution, but we don't need isotopic resolution to identify anything. We just, oh, that was another thing. Here, in reflector mode, we have to do our peak-to-peak comparison from the monoisotopic mass. That's critical because otherwise we'd pick an arbitrary peak in the isotopic envelope. So the difference in linear mode is instead of having a monoisotopic mass to identify, because of the reduced resolution of linear mode, we're just looking at whole oligomers. Each single peak is a whole oligomer. But we can do the same exact thing. The distance between oligomers is the mass of the monomer unit. So in this case, it's polystyrene. So remember I was talking about distribution, MALDI. See how we have a whole envelope of a bunch of oligomers and a variety of molecular weights that overall contribute to a polymer molecular weight distribution. The beauty of this technique is this is the only technique where you're going to see resolution to that degree. GPC, you'll see just a trace curve over essentially the tip of all of these peaks. So MALDI is the only technique where we can actually distinguish individual oligomers and be able to identify materials that way. So it's really, really, really cool. And this is, you can notice, this is actually fairly high, decently high molecular weight to get oligomeric resolution. So, but we have to have oligomeric resolution at minimum in order to use this to identify a particular polymer. Polymer spectrums in MALDI are affectionately called the MALDI-saurus. So if you ever have any biologists use MALDI and see polymer contamination, they might mention that in disdain. But us polymer chemists like to see this kind of spectrum. Okay, so we want to do N group analysis because that's super important. N groups of your polymer might imply a lot of different functionality or the ability to do chemistry on those polymers. So this is kind of the old school way of doing N group analysis, where we take some mass data and we fit it to just a simple y equals mx plus v fit, where x along the x-axis is our degree of polymerization. We've just selected a couple peaks. And then y is our total molecular weight of each oligomer as measured by MALDI, so everything included. And so we can separate out the N groups from our full mass, because if we say if the slope is the monomer weight, then what we can do is back calculate to 0 to get a y-intercept as what if there were no monomers. And if we had no monomers, what would we be left with? Just N groups and adducts. If we know what adduct we added, like a sodium or a silver, we can subtract that out and say, hey, our N group mass is, let's say in this case, 269.06 minus the 23 of the sodium, and then we're left with the mass of N groups that we can then figure out what they are or confirm what we know, what we think they should be. So you can do it that way. You can do it a little easier using poly tools. This is a tool by Brooker that helps us to take polymer data and basically does that for us without us having to do things in Excel. And so what you'll see here is we can give it some information like, hey, I think this is polystyrene. If it is polystyrene, it will agree with you. And your peaks here in this Kendrick mass defect plot will be, or your plot here, everything will be horizontal if it agrees with the monomer mass that you've assigned it. Otherwise, you can let it predict that. And if it's spot on, it will tell you what monomer it thinks it is. And then basically what we need this software to do is get the residual down to 0. So the residual mass, what's that left over? That plus b in our y equals mx plus b. If we can get our residual mass to equal 0, then we've accounted for all of the mass in each polymer chain. So in this case, I took a polystyrene polymer and it gave it enough information to have it make assignments, and then it agreed with me that my N groups were what I thought they were. The nice thing is it also, in the process of telling you what your N groups are, it also will give you a number average molecular weight, weight average molecular weight. Here, this PD is dispersity, and DP is degree of polymerization. So we've done a whole suite worth of polymer characterization in 5 minutes of acquiring some data and throwing it into PolyTools. You do this with other techniques that can take many, many hours of analysis and instrument time. So if this technique works, you can do amazing things with it. Okay, so polymer analysis. If we've got, let's say, a large copolymer, large polymer that doesn't have a logarithmic resolution anymore, we can still get some really interesting information out of it. This is a copolymer that I ran on the MALDI where I was able to see a nice distribution, but no oligomeric resolution. Okay, but so why does that matter? Well, this is the only way for me to get an actual accurate mass of this particular polymer without running a universal calibration on GPC, which may or may not be possible depending on what type of instrument, what type of capabilities your instrument has. So for me, this was a lot easier to get an accurate mass on the MALDI versus trying to do many hours of GPC runs and calibration. The reason being is because we have a mix of 2 different types of monomers, standard homopolymer calibration on GPC won't help us get an accurate molecular weight here. If you can do N group analysis on NMR, you can get a fairly close molecular weight for this, but it won't be as accurate it won't necessarily be as accurate. So let's say, I want more than just a molecular weight. I want a little bit of characterization about this polymer. Well, we can do some tricks where, I don't have a logarithmic resolution, but I can actually get the software to arbitrarily assign peaks to this. So you might notice they're all just spaced 100 Daltons apart. These are not real peak assignments. It's just so we can take this data and put it into PolyTools and get some analysis out like this. So I can take this polymer and by making essentially fake peaks along the distribution, we can get a number average molecular weight, weight average, dispersity, and degree of polymerization. That actually is not particularly accurate because we don't have the combination. So ignore the degree of polymerization, but we can get MN, MW, and dispersity, which is really helpful for a polymer that you might not be able to characterize in other ways. Okay, so some other interesting things we can do with polymers. We can confirm structure. So the Chen group does a lot of cyclical polymers, cyclical recyclable polymers, lots of really interesting polymer chemistry there. It's hard to, if you have a linear or cyclical polymer that have the same molecular weight in GPC, they're going to look exactly the same. In MALDI, because we can do N group analysis, we can analyze this polymer and in the end realize, okay, what's our residual mass? Well, it's actually just the mass of the sodium cation that we added on to the sample to ionize it. And we can confirm there's no N groups, which is really, really helpful for when you're trying to figure out applications or figure out what kind of chemistry can you do with this sample from here on out. So, okay, so enough about polymers. Hopefully you think polymer chemistry is cool now. But a lot of other things we can do with the MALDI, it's not just limited to polymers and synthetic materials. We can analyze peptides. In fact, peptides are probably one of the most common uses of this instrument in the industry. And so, just as an example, this is a peptide mix that we use for calibration. The peptides give us really nice, well-defined, high-resolution peaks. We can also look at protein digest, so peptides of protein digest. So this would be like enzymatically digested protein, and then we can see all the peptide fragments that are part of that digest. And then, you know, really nice high resolution data here, all isotopically resolved in the peptide spectrum. We can do MSMS of peptides. That's a pretty common application. If we take a BSA digest, we can then select a particular mass. So in this case, I selected this peak at 2045, isolated that using the lift function, and then fragmented. And then this is the spectrum of all the fragments of 2045. Then we can take that spectrum and load it into a tool called BioTools, where it will help us sequence it and do database searching. And that looks like this, if you've ever used Matrix the Matrix database to do protein and peptide characterization searches, that your results might look like this, where I took this BSA digest and I imported just the spectrum of this 2045 fragment, and it was able to search and confirm that it's bovine serum albumin. Is that a good score or bad score? I don't know. I'm not I don't do proteomics, but I know that it works. Okay, so proteins, a lot of people use the MALDI to measure intact proteins. This is an example of Chuck Henry had a class where they wanted to measure degradation of casein. And so in this top spectrum, we're looking at the intact mass of casein. So here you've got your intact +1 mass. And this peak at actually 11,800 is our +2 peak of casein. And then they aged the casein, I'm not sure how, maybe heat or time or whatever, but that you can see that the intact protein mass really, really goes down, and we actually start getting a bunch of protein fragments. But also the interesting thing is that the mass actually shifts up, and my theory is that it's probably oxidizing. So you're getting a mass shift with a bunch of oxidation on the protein, of what's left of the protein. And then this is an example of a protein that ionizes really nicely in MALDI. It's a carbonic anhydrase that we use as a calibrant. This is nice, really clear, well-defined peaks. Last application I want to talk about real quick is oligonucleotides. We have a collaborator, Marino Resendez in CU Denver. He studies and makes synthetic oligonucleotides of RNA. He's measured some, one of the applications is he's measuring these oxidative lesions in the in an RNA sequence, and then he sends us samples and we measure an accurate mass on MALDI, either an intact RNA fragment or the 2 cleaved fragments of that RNA. Really cool application. He's been working with us a long time. We appreciate him. Okay, so let's just real quick breeze through the ARC and all of the instruments we've got before we run out of time. So at the Analytical Resources Core, we have Materials and Molecular Analysis Center, where we have all self-use NMR, mass spec, materials analysis spectroscopy, UV vis, X-ray diffraction. All my colleagues are really amazing and they're all really good at what they do. So if you ever need any help with any of these things, please talk to them. We also have self-service, all of these instruments are available for full service as well. Self-service electron microscopy and surface analysis. And then our full service lab does metabolomics, proteomics, ionomics, cheminformatics. Everyone at the ARC is super awesome. So hopefully you can take advantage of our services. If you're interested in self-service mass spec, these are our offerings. We have an ICP-MS, we have a bunch of GCs, single quad, thermal desorption, single quad, triple quad. We have 2 MALDI-TOFs. If you want a benchtop MALDI, that one is for sale. And we have a walk-up UPLC that's really cool because we can use it with a couple different sources, an ESI source and a DART source. Our organic chemists love the DART source because it's super quick and fun. You just stick samples right in it. Okay, and then this would not be a proper talk if I didn't give a shameless plug to the School of Materials Science and Engineering Materials Core facility that I manage. So if you have any need of materials science equipment, We have a ton of really cool materials processing capabilities, a mini injection molder and microcompounder for small batch polymer processing, laser cutter for making samples, fabricating samples or devices. We have a thermoformer, spin coater, filament extruder, and we have a whole bunch of thermal processing equipment. We're also thinking about getting a 3D printer for making molds for the injection molder or various other fabrication tasks. We have a bunch of awesome materials characterization equipment, including a brand new mechanical tester and a brand new rheometer that can do wide variety of thermal analysis, wide temperature range of analysis of your materials. We have we have 2 GPCs, we have a hardness tester, and then we're working on setting up a 30-liter air-free reactor for anyone interested in materials in reaction scale up. We'll have a schlank line, a solvent column, and a solvent recycling system. So, you know, lots of, if you don't have the capabilities to do this in your lab, you'll be able to rent the space out of our core. So really cool and coming soon. Just want to thank everyone who's kind of helped out along the way. Caroline Denef being driving for Caroline and Travis being the driving force in acquiring the Ultraflex. Claudia was also PI on that grant and is my boss, and she's a wonderful person. Kitty, she's no longer with the ARC, but she's amazing, and she taught me how to use the MALDI to begin with. Gwen is an undergrad at our facility, and she's just so smart and so awesome, and she helps me out with the MALDI all the time. This talk and everything about the MALDI wouldn't be possible without all of our amazing Ultraflex users, particularly the ones who gave me data to talk about in this talk. Thanks, Travis, for teaching me everything about polymers, and every other PI that support the Ultraflex and keep it going. And then everyone at Brooker who helped, you know, train me, install the instrument, help us coordinate all these amazing seminars and things we've had. You know, Brooker has been a really awesome partner to work with there, and everyone who works there is really great. So appreciate everyone who's helped out. Okay, that's it. Do you have any questions? Sorry, I went really long, but we have like 2 minutes for questions.
Please chime in. Raise your hand if you choose, or go ahead and jump in.
Hi, Alyssa. This is Paul.
Hi, Paul.
Nice talk. Thank you.
Thanks.
You know, we have a lot of like accurate mass work at ARC MMA.
Mm-hmm.
We often run into just like problems or like taking a lot of time just figuring out ionization. Do you see the MALDI being like a good workflow to do accurate mass requests?
Yeah, so yes and no. I think yes, because we can definitely get accurate masses, and it can be really great for certain small molecules that don't ionize any other way. A good example of small molecule accurate mass I didn't show here would be the Miyake group does photocatalysts, and so we can get really nice accurate mass for those. The tricky part is this sample prep can take a lot of time to troubleshoot. So, you know, some customers, they don't want us to spend 3 hours of staff time to figure that out. And then the other tricky part is that, you know, in order to get a lot of things to ionize, you have to have a matrix, which is also a small molecule. So sometimes the small molecule spectrum can be kind of convoluted. And so in a best case scenario, the small molecule you have just happens to ionize really well, and all the other stuff in your spectrum gets kind of almost ignored because your single molecule just is ionizing so much better and more intensely than everything else. So it's a good option. I would say more is the last resort for accurate mass and less of I wouldn't ever try it first just because it can take so much time.
Gotcha, thanks.
Other questions?
And I can't see the chat, so if there's any questions in the chat, let me know.
Okay, I think we have a satisfied group. Obviously, if you have questions in the audience, you can always reach out to Alyssa after the fact. I'll thank everybody for coming, thank Alyssa for presenting, and I hope to see you all at our next seminar. Thanks, everyone.
Thank you very much for coming, everybody.